Hello, this is Grace Seay, presenting Project 3 for Design and Manufacturing at Georgia Tech. In this project, I will discuss the design and manufacturing techniques and processes that I found the most interesting. The subjects that I have selected are thread and gear rolling, incremental forging, boring and boring machines, centerless grinding, and water jet machining. The first technique that I have selected is thread and gear rolling, a cold forming process that forms threads on round parts, such as a rod or wire, by passing them between reciprocating or rotating dies. The teeth on the die press against the surface of the workpiece and displace the metal to form the threads. Spur and helical gears can be produced by processes similar to thread rolling. Thread rolling is an important process because of how widely it is used in the manufacturing of basically all externally threaded parts. The threads it forms are superior to machined threads in terms of strength, fatigue, and the amount of material required. Thread rolling is used to make almost all externally threaded fasteners, including screws and bolts. Gear rolling has numerous applications in automatic transmissions and power tools. The capabilities of thread and gear rolling are that it can produce threads extremely fast, with a smooth surface, resistance to fatigue, and higher strength threads due to their grain flow pattern. It also requires a round stock of smaller diameter to produce the same major diameter as that of a machined thread, and avoids wasting material since the threads are not cut out like machined threads. Thread rolling can also be done internally with a fluteless forming tab, and produces accurate threads with good strength. The limitations of thread rolling are that it does not work well on brittle materials. The machines also have a higher startup cost than machined threads, and they typically have a limited range of thread sizes, so they are less versatile than forming threads by cutting away material. The next topic I have selected is incremental forging, a process in which the workpiece is deformed repeatedly to form its final shape. Since the deformation is done in steps, the forces applied in incremental forging are much lower than in conventional forging. One type of incremental forging is orbital forging, which has the die move around the workpiece in an orbital path. Incremental forging has applications in making things out of sheet metal with high precision or customization, such as panels for planes or cars, or highly customized products, such as medical implants. Since incremental forging takes place over multiple steps, the forces applied by the die are lesser in magnitude, which means that the die lasts longer than in other forging techniques, and the operation is quieter. The incremental nature of the process means that the same die can be used to forge similar parts instead of requiring a specific die for each design. This makes incremental forging cost-effective for smaller scale production. It also allows for changes to be made to the product design very quickly and easily, unlike with other processes such as deep drawing, which would require an entirely new die to be manufactured for each new design. Of course, any process has drawbacks. Since incremental forging is incremental, it takes longer than other processes such as deep drawing, making it less optimal for large-scale production. This process also takes multiple steps to form right angles, making it better for more rounded designs. I chose to present on incremental forging as one of my topics because it is the most unique of all the forging techniques, and also because it allows for more flexibility and customization of the design compared to other forging processes. Another topic that I found interesting is boring and boring machines. Boring is the process of enlarging a hole made by a previous process. It can also be used to produce internal profiles or grooves in hollow workpieces. Either way, a hole must already exist in the workpiece. Boring can be done using a lathe or a boring mill to guide the position of the boring tool, depending on the size of the workpiece. A lathe is used to rotate a smaller workpiece as the boring bar is inserted into the hole, while a boring mill holds a larger workpiece stationary and the boring bar rotates. A cutting insert, which is attached to the boring bar, cuts into the workpiece to enlarge the existing hole. Boring can be thought of as the internal diameter counterpart to turning, which cuts external diameters. Boring has applications in manufacturing engine cylinders, gun barrels, and many parts used in the automobile industry. Boring machines are important because of their high precision in making smooth finishes. The process can be done on a variety of machines, and boring-specific machines can also be used for turning, basing, grooving, and chamfering. Boring is great for increasing the diameter of a hole with high precision and tight tolerances. It is also a very fast and versatile process. The same boring tool can be used for different size holes, and the cutting inserts can be easily replaced. Limitations include reduced stability of the cutting tool relative to turning because the cutting tool goes inside the workpiece, causing it to be held less rigidly and have increased clearance angle requirements. Since the boring bar has to reach the full length of the bore, tool deflection and maintaining dimensional accuracy can be a concern. Boring is better for through holes rather than blind holes, since a boring bar can be supported on both ends for a through hole, but only on one end for a blind hole. Boring also produces finishes that are less smooth than reaming. However, the limitations of boring in terms of its geometric accuracy has been shrinking as machining technology continues to advance. Another important manufacturing technique is centerless grinding, a process in which material is removed from a cylindrical workpiece using abrasive cutting. In centerless grinding, the workpiece is supported by a blade instead of by centers. It is then ground between two wheels, the larger of which actually does the grinding, while the smaller wheel regulates the axial movement. Centerless grinding can be classified into three main categories: through-feed grinding, plunge grinding, and internal grinding, each with their own capabilities and limitations. Centerless grinding has applications in manufacturing sleeve or ring-shaped parts, such as cylindrical roller bearings, piston pins, engine valves, and camshafts. Parts with variable diameters, such as bolts, valve tappets, and shafts, can also be ground by centerless grinding. Centerless grinding is important because it is a grinding process that prevents deflection of the workpiece better than other grinding processes. Through-feed grinding is very fast because the pieces are auto-fed through the wheels without being manually pushed. It is good for grinding cylindrical objects, but bad for complex shapes. In-feed centerless grinding is highly adjustable and good for complex shapes. However, the grinding wheel must be set up for the shape and size of each individual piece, and each piece must be fed in manually. This makes it not recommended for mass production because it is much slower than other grinding processes. End-feed grinding is best for working on objects with tapered surfaces, since its auto-feeding decreases the diameter of the entire piece instead of just one single aspect of the piece. Overall limitations of centerless grinders include difficulties working on pieces with right angles or short pieces with large diameters, since they are difficult to control between the grinding and regulating wheels. For my last topic, I will be discussing water jet machining. This technique uses the force from a jet of water to cut grooves in a material. This technique can be done using water with or without added abrasives. Pure water jet machining is intended for use on softer, non-metallic materials such as plastics, fabrics, rubber, wood products, paper, leather, insulating materials, brick, and composite materials, while abrasive water jet machining can cut metals. Both processes can also be done on multiple axes when guided by robots. Water jet machining is important because it is the optimal machining technique for manufacturing highly sensitive parts. Water jet machining has applications in the mining and aerospace industries for cutting, shaping, and reaming, and also in the food processing industry for cutting and slicing food products. It is the preferred method of cutting materials such as plastic and aluminum, which are highly sensitive to the high temperatures generated by other methods. Water jet machining is capable of efficient and clean cutting as compared with other cutting processes. Cuts can be started at any location without the need for pre-drilled holes. Since it causes no deflection of the workpiece, it is optimal for cutting flexible materials. Pure water jet machining is also environmentally friendly, since it only uses water, but abrasive water jet machining is less so, because the water contains abrasive particles such as silicon carbide or aluminum oxide. The main limitation of water jet machining is its cost. Not only is the equipment expensive to purchase, but it is also expensive to operate. Therefore, it is typically only used for machining workpieces that require extremely precise cuts or have high flexibility or sensitivity to temperature.